Hello, I'm Marco Kellner and this is Lab 5 for Choosing Our Own Adventure. For this lab, I decided to use projectile motion. So the purpose of this lab is to use the energy principle and Newton's second law to analyze the motion of a weighted projectile. I'll be throwing a basketball to one of my friends and he's going to catch it, and I'm going to put that video into Tracker and analyze its motion. In the end, my results showed that the model prediction showed a close resemblance to the observed motion, but with a few discrepancies, which I'll explain later. So here's a preview of the major sections. I'm going to go in a way that it's the easiest to understand. So here's a video of me throwing the basketball at my friend. It is a small basketball and it's easy to catch. And it was only 16 frames, and it gave us this information over here, which I exported it to an Excel file so I could analyze the information. So this is a chart with the information that Tracker gave us. The Y position is the one that curves like an upside down parabola. It peaks at this place here. But the X position, since there's no external force acting upon it, it goes in a gradual increase as time goes by. So finding out the velocity so that I can use it in the VPython code. For the X, I just used the average slope of the X position line in the previous chart divided by the fraction of the second that each frame measured. So 0.0477 was the average slope, but since it's not in meters per second, I had to divide it by by how many seconds and how many frames it was, and that gave us 1.156. To find out why, I used the energy principle. So the potential gravity was equal to the kinetic energy initial. After plugging in the numbers, I got velocity initial is equal to 3.25 meters per second. So I'm going to show you the code right now. Here, this is a simple initialization, and here's where I put the velocities. It starts at the 0, 0, 0 at the origin, and I use a small time step delta t. So the only force acting upon this is the gravity, and here's the ball.vel is where we use the Newton's second law. So the velocity final is equal to the velocity initial plus the F net divided by mass times delta t, and the position of the ball was updated with as time went by multiplied by velocity. Here's a comparison of the two models, the VPython model and the observed motion from Tracker. You can see that they're closely resembled, but the one in the observed motion does not reach at the end because my friend caught it before it reached a negative Y value. I believe the model almost reaches 0 Y value, surpassing the observed motion because it didn't take into account air resistance. And drag force actually affects differently as the thing's going up as opposed to when it's going down. So in conclusion, we were able to find out the initial velocity with observed motion of the projectile using the energy principle and Newton's second law. So the discrepancies can be explained by air resistance, and since I don't really understand how air resistance affects the ball as it's going up, I only know when it's going down, it would be an interesting thing to look forward into. Thank you for listening.